Okay, howdy. So now we'd like to talk about magnetic moments. What do I mean by magnetic moment? Well, if you had a bar magnet, which you may or may not have seen in the past, I suspect you have, sort of like that. That'll have a north and a south to it. Well, the magnetic moment is the way we talk about that in physics, all right? So the magnetic polarization, the magnetic, or we'll talk about that in a second, but the magnetic moment, and we'll call that little m, points from the south pole to the north pole of the magnet, and eventually we can pretend like we have a dipole, just like we had with the electric dipole, which is a big reason why I talked about the electric dipole. So this permanent magnet, has that magnetic moment. So we'll talk about how we get those magnetic moments. They're really how objects interact with fields, with the exception of the charge. A moving charge interacts with an electric field. And I probably gave you a couple of links that explain that already. So you might want to look at those. They're fun. And so this thing here is our paradigm of what happens, is that we have something like this bar magnet. So we're going to pretend like everything in the world is a bar magnet, which is pretty lucky because more or less an electron is a bar magnet. And we'll talk about that in just a moment. In fact, if we have a bar magnet, then what we call the unpaired electrons in a material, so might have an energy level diagram like this, right? So you have your energy up here, then you have your electrons that have a magnetic moment going upwards, and electrons with a magnetic moment going downwards. This is how we populate the atom, right? Is we first say, okay, well, we go to the lowest energy level and we put an up atom in there, and then we put a down atom in there, or up electron and down electron. So actually that cancels out as far as the magnetic moment is concerned. And then go to the next level, and up and a down. Next level, and up and a down. And then maybe we'll get to a level where we have an up, but we don't have any down. That is my unpaired, uncompensated electron right there. That is this electron right here. Let's find a pretty bold color here to highlight it. This electron right here, with its magnetic moment going up, that guy is the guy who's going to create the magnetic moment of this entire bar magnet. So for your permanent magnets, what happens is that inside of here, each atom will contribute by pointing up. Now this only happens for a few different elements. Iron, cobalt, and nickel are the big ones. There's rare earths like neodymium and and stuff like that. I hope I pronounced that right. And this thing produces a magnetic moment. So you add up all of these little baby moments. Each one of these electrons has a magnetic moment, let's say mu. And you add them all up and you get the same dipole moment that you get here. So these are the same thing, because these are the same thing. Add them all up, you get your magnetic moment, and that is your permanent magnet. Now, again, only special atoms correlate these different electrons, make them align, but other atoms have the uncompensated, or other materials have uncompensated electrons. They just aren't coupled like this. They just don't have what we call exchange coupling that you have here, that sort of acts like a little torsion spring that tries to get everything aligned. So we'll talk about those next in part 2. But here we just want to talk about what makes up this whole magnetic moment thing here. And that's just what we said, permanent magnets. Dipole moments. Come from the moments of the elementary or the aligned uncompensated electrons. Remember, uncompensated is this little gold thing up here. Maybe I should do that. Can I make it? No, I can't. Okay, so the aligned uncompensated electrons. That seems fairly simple, and actually that makes how we write this nice and easy, right? The magnetic moment is equal to the number of uncompensated electrons in here times elementary moment, which is basically the Bohr magneton. There's a little bit of an issue with that, but we'll ignore it for the level of this class. Later classes you might not have to, but for the level of this class you get to ignore it. You just say, okay, everything, the elementary spin or the elementary magnetic moment is this Bohr magneton, named after Niels Bohr. If you go to Houston, there is a bar called the Niels Bar, which I haven't been to. When I was young and I was running around Houston like a crazy person, it wasn't there yet. And now my wife won't let me go. So that's minus 24 joules per Tesla. Okay, so that's the value of that thing there. Uh-oh. I hope that's right. I didn't see that because I accidentally erased my mark. Told me how far I can go down. Oops. So that's it. I mean, that's basically all you do. So then we say, okay, we have another way of talking about this, which is each material has sort of a density of atoms, right? So we can talk about the volume average moment called the magnetization. That's equivalent to the polarization of a electric material, a dielectric material, or a ferroelectric material actually. Magnetization of a ferromagnet. We call these ferromagnets because iron is the paradigmatic example, not because it necessarily has iron in it, although a lot of them do. Again, cobalt or nickel is also common. Is its volume average moment. Now there are some cool things that go along with this. I'd love to talk about them, but they're a little advanced. Let's see. Okay, and I have to warn you. So I said we can pretend that there are charges here, but there aren't ever really going to be charges. So in the very last lecture, I'll give you the way that we pretend like we have charges on this, because it makes calculation simpler, right? But that's all it is a way to do math. There aren't any charges on either side, or to be more precise, there are no unpaired or isolated magnetic charges. Okay. So that just means that whenever you see a north pole, you'll see a south pole pretty nearby. And that's technically because every electron, which is as close to a point particle as we know about, right? Said it's less than 10 to the minus 22 meters, is already a dipole moment, right? So when we add up these dipole moments, we're actually adding up things that are not or do not have north and south poles. Okay, so the north and south pole is just sort of an approximation that we use for something that's really big, because the minuses and the pluses cancel out in the electric dipole, so it's somewhat similar, right? But never get confused. Don't get confused. There are no real north and south poles to a magnet. In the real world, that would be a charge, and there are no charges that go along with magnetism. All right? If there were, life would be easy, life would be great, I think, and so forth and so on. People try to find magnetic monopoles all the time, because there's no reason why there couldn't be that anybody knows about. There's no reason that there couldn't be magnetic monopoles as far as anybody knows about, and if there were magnetic monopoles, all sorts of good things would happen. It's just that nobody's ever found one, so we don't really believe they exist. Except in materials, you can do anything in a material. So, but then it's a fake monopole. We can talk about that in class if you like. So, that is the stuff that's going on in your permanent magnet. This is why you have things that can stick to your refrigerator. Now, every other material also responds to a magnetic field, just like they respond to an electric field. And then you have different kinds of magnetism called paramagnetism, which is when you have uncompensated electrons that don't have this coupling that causes them to align. And you also have diamagnetic materials, and those only have compensated electrons. And so something else, there's a little different physics that shows up in how they respond to a field, and actually that's going to make them respond differently than the paramagnetics. We'll talk about that next time. And after we're done with that, we'll talk about the way we can construct a magnetic field, or a magnetic moment, 2 lectures hence. We'll talk about how we do that sort of in the lab, let's say, with an electromagnet or something like that. How does that work? That'll be the last lecture, or the last segment for this lecture. All right? Bye now.